So this is continuing chapter 20. And so now I'm going to go over a little bit of what this E voltage means from your reduction potential table that I pointed out to you. And you might want a highlighter. I'm going to highlight a couple things on your notes here. So the cell potential, again, the whole point of doing this is to get some electricity. So we need to understand how much are we getting out from each particular cell. So the cell potential is the pull or the driving force on the electrons. So sometimes it's called the electromotive force, EMF of a cell. We are going to focus it on the fact that a volt is 1 joule of work per coulomb of charge transfer. So we're going to talk again about coulomb a little bit more specifically in terms of a calculation. So when we have our galvanic cell, we have a voltmeter attached or a multimeter if you're again familiar with it from physics. We can measure the difference in what we call the electrical potential between those two half cells. So what we have is that standard reduction potential, that's the table that I showed you. And we can use that to find what we call the E cell. So again, the little degree sign, capital E, degree sign means we are at 1 molar concentration, 1 atmosphere of pressure, and 25 degrees Celsius. So again, that has been our standard temperature and pressure for a while. What is different now is the 1 molar concentration. And we will talk a little bit later on about if we're not at 1 molar, what do we need to consider with that? So we can find what we call the E cell. So we have 2 different half cells that add together. So there are 2 different ways of approaching what we call the cell potential. So the E cell potential is going to be the combination of the anode and the cathode. So this first example here is really how I do the calculation, but technically you could do it either which way. So let me use copper as the example, copper and zinc. We have copper 2 plus 2 electrons goes to copper, and then I have zinc goes to zinc ion and 2 electrons. Okay, so I'm going to use that as my example. So if I go back to my table, I will see the copper 2 plus has a voltage of 0.34 volts. Okay. And if I look at the zinc, I realize that zinc is written as a reduction, so that's a negative 0.76. So I have to flip the reaction. So in order to do that, I need to follow some rules associated with these potentials. So anytime I reverse a reaction, I change the sign. So I'm going to change this to 0.76 volts because this is an oxidation reaction, not a reduction reaction. So with the cell potential, okay, I take the one that's being reduced, okay, this is being reduced, and I add it to the one that is being oxidized. So I flip this reaction and write it as an oxidation reaction. So when I do that, I get a voltage of 1.1 volts. Now, in the second equation, it has the reduction of the cathode, so that has the 0.34, but then it has minus the reduction at the anode. So again, if zinc is the one that's being oxidized, but it is the other reaction in this cell. So if I took 0.34 minus negative 0.76, I'm going to get exactly the same answers. Okay, so you're subtracting the other reaction that's probably negative. Okay, and again, what the negative means is, okay, if you look at this table, it means it does not want to spontaneously take on that electron, okay? So that's not as favorable in chemistry. So what happens if I don't have equal numbers of electrons and I need to multiply by a factor? Well, a big idea that kind of gets lost in translation here is the E does not change, okay? The voltage is the voltage. It's always going to be determined on that pull on that electron. So again, the overall multiplication of it is going to be indicative of one is going to want 2 electrons, so it's going to pull 2 electrons from that. So this is always not going to change in terms of the number that you see. So let's try a practice problem or 2 so you can kind of get familiar with how you do this. So let's say I have lead 2 plus ion and lead solid, And again, I'm not putting them in any order, so I'm not dictating which one is oxidizing, which one's reducing. And then copper 2+ as my aqueous, and then copper solid. So what you have to do is look at your table and figure out who's further up, who's going to be reduced, and who's going to oxidize. I'm going to pause the video and then come back and show you the answers. Find the voltage for that. All right, so if I look at copper versus lead, okay, lead 2+ is -0.13 and copper has a positive 0.34. So copper is going to be the one that reduces. It's further up on the list, so it's going to be 0.34 volts, and you write it as a reduction. So lead, you're essentially going to flip it or make it an oxidation. So lead's going to become lead to ion, and you're going to change the sign of the voltage from negative to 0.13 volts. When I add it all together, okay, I have my copper 2 ion aqueous plus lead solid goes to copper solid plus lead 2 aqueous. And again, order does not matter. And then all you do is add up the voltages. They're both positive. Now, again, you can take 0.34 minus the negative 0.13. You get exactly the same answer. So see if you could write the line notation for this just to get the practice. So here is the line notation. It's the lead plus the lead ion. This is your anode. Copper 2+ goes to copper. That's your cathode. And again, that's just extra practice so you get familiar with that. All right, so to summarize galvanic cells, okay, do understand that the cell potential will always going to be a positive value. So the voltage that you get will always be positive. If it isn't, you probably flipped the wrong reaction, okay? And again, that's your E cell. So just so you see it multiple ways, multiple times. Electrons are always going to flow from the anode to the cathode. So the one thing I didn't emphasize too much back a couple pages ago is the fact that the electrons always flow in this direction. They always flow from the anode side to the cathode. Anode side to the cathode side. And if you have any need for any chemically inert electrodes, you want to use platinum. Hydrogen can also be used, but you do need some kind of inert metal in your system in order for that to work. So for this next part, I want you to make a chemical cell from these components, and then I'm going to have you do a couple different things with it. So one of them is going to be magnesium 2+, and then the other one is going to be aluminum 3+. And I'm not putting them in any order, with a piece of magnesium, a piece of aluminum. So I want you to write the net ionic, so you need to write out the two half reactions and add them up. I want to know the voltage, okay? And then also give me the line notation to kind of get the practice. Line notation. All right, so I'm going to pause the video and come back and show you the answer. All right, so your voltage for this one comes out to be 0.71 volts. Again, the magnesium is going to be the one losing electrons. Aluminum is going to gain depending upon where it is on the list. So magnesium is higher than aluminum on that reduction potential. So it's going to be the one that aluminum is higher than magnesium, so it's going to want to reduce. So you end up with -71 volts. In order to balance the electrons, you needed to multiply by 2 and multiply by 3. So in your line notation, please be sure that you do include the balancing as well. So whatever is in front of your net ionic equation needs to be included in your line notation. We haven't had many examples of that, so that's why I use this for that as well. So the next two problems are just same kind of thing. It's just they're in different formats. So calculating the E cell for the following reactions. So sometimes you might be given a balanced chemical equation. So you need to kind of look at it and see who is losing electrons, who is gaining electrons. Now the good news is you don't need to look at the table to see who's further up. You just need to look at the reaction. So zinc is going from a 0 oxidation state. Make this a little bigger, to a 2+ oxidation state in zinc chloride. And Cl2 by itself would have a 0 oxidation state, and in a compound it would have a -1. So obviously zinc is undergoing oxidation and chlorine is undergoing reduction. So see if you could write out the two half reactions and find the E cell for this reaction. I'm going to pause the video. All right, so if you're just looking for the E cell, it would end up being 2.12 volts. Again, the zinc would be 0.76. The Cl2 going to 2Cl minus would be 1.36, and when you add them together. So here is the net ionic equation. And I wrote down here the line notation because it is a different kind of line notation. So again, zinc and zinc ion, that's never, we've done a few examples of that, but this is Cl2 gas and Cl minus aqueous. So this will need some kind of metal in order for the electrons to transfer. So again, put platinum, put another line and platinum and a solid on the outside for the line notation anytime you don't have a metal somewhere on the anode side or the cathode side. Again, if it was over here, you draw a line and put platinum first. And this is my scribble there. It's just a straight line. I just had a hard time writing it. All right, so one more problem is this next one. Find the standard reduction potential for Cd2+ to Cd electrode from the following reaction. So I'm showing you this one because they don't give you that reduction table anymore on the AP test. So they might ask you to find one of the electrodes by giving you the whole cell and then giving you one other one. So please write down Cu2+ plus 2 electrons goes to Cu is 0.34 volts. So they might give you a line notation like this, and you have to understand that this is your anode and that's your cathode side. So that understanding that the cathode, you're going to have the cathode being reduction is going to be the copper. So that's going to be the 0.34. So you have the 0.34 volts plus something is going to give you 0.74 volts. So again, this is just a different way you might see it on the AP test. So I just want to kind of expose you to that. So the CD is becoming Cd2+, but realize they want you to go from Cd2+ to Cd, meaning they want it as a reduction. So this has to be 0.40 volts in order to get to 0.74 volts. But your final answer needs to be negative 0.40 volts because they're looking for the reduction potential for that Cd2+ to Cd. So again, just showing you another example of how you would see an E cell type calculate.